Calculating Kc, the equilibrium constant. There are 6 steps to calculating the equilibrium constant. The first is to write a balanced equation. Then we must draw a table, which I will show you later. Then we must calculate the moles for the chemicals given. Then we must work out the moles at equilibrium. Then we must calculate the concentration of all the chemicals. And finally, we can calculate Kc. Here we have a question. Iron 2 sulfate and silver nitrate react according to the following equation. 25 centimeter cubed of 0.1 mole decimeter to the minus 3 of iron 2 sulfate and silver nitrate were mixed and allowed to reach equilibrium. The unreacted silver ions were then titrated using a 0.06 mole decimeter to the minus 3 potassium thiocyanate solution, giving an average titer of 2 centimeters cubed. So first we must write a balanced equation, and this equation is already balanced, so we don't need to do that. Then we must draw a table, which I was talking about earlier, where Ni is the initial number of moles. This is the number of moles when the reactants are placed into the reacting vessel at that initial point when basically 0 seconds have passed. And then we have N at Eq, where Eq stands for equilibrium, which is the number of moles when the reaction has reached equilibrium, and using this we can calculate the concentration at equilibrium, C at Eq. So now we must calculate the initial number of moles. You may be able to see that from my Fe3 plus has actually got 0 because it's not actually being produced at the beginning of the reaction. It only happens when the reaction takes place. So therefore at the moment there's no moles of Fe3 plus being produced. We now calculate the moles for the chemicals given, that is the iron 2 sulfate and the silver nitrate. And we do this using the N equals Cv equation. Here's the working out, which is 0.1, which is the concentration, multiplied by 25 centimeter cubed divided by 1000. We need it in decimeter cubes, therefore I'm dividing it by 1000. And we get 2.5 times 10 to the minus 3 moles. And this is the initial number of moles for Ag+. And Fe2 plus will be the same, as you can see by the stoichiometry of the equation. Now we must work out the number of moles at equilibrium. As you can see in the top right hand corner, the box has actually changed to green because we're using a different part of the question. And the bit of the question we're now using is that the unreacted silver ions were then titrated using a 0.06 mole decimeter to the minus 3 potassium thiocyanate solution, giving an average titer of 2 centimeters cubed. We use the N equals Cv equation in the following way to work out the moles at equilibrium for the A silver plus ions. And that is 0.06, which is the concentration, multiplied by 2 divided by 1000, which is the volume, giving us 1.2 times 10 to the minus 4 moles. And this is the moles at equilibrium for the silver plus ions. Looking at the stoichiometry, the iron 2 plus ions will be exactly the same. And now we must calculate them for the Fe3 plus ions. In order to do this, we take the silver ions that were present at the initial, at the start point, and we minus from them the moles that were present at equilibrium for the silver plus ions in the following manner, which gives us 2.5 times 10 to the minus 3 minus 1.2 times 10 to the minus 4. And this gives us 2.38 times 10 to the minus 3 moles. And this is the number of moles at equilibrium for the iron 3 plus. So now we must calculate the concentration of all the chemicals using the formula C equals N over V. As you can see at the top, the box has actually changed back to the original one, and we have the original part of the question that we had earlier on. So to calculate the concentration of Ag plus at equilibrium, we do it in the following manner. we do 1.2 times 10 to the minus 4, which is the moles at equilibrium, divided by 50 divided by 1000. The reason we do 50 centimeter cubed instead of 25 is because in the reaction vessel we have 25 centimeter, we have a 50 centimeter cube solution, 25 centimeter cubes of iron sulfate and 25 centimeter cubes of silver nitrate, therefore 50 centimeter cubes. So we do 1.2 times 10 to the minus 4, which is the moles at equilibrium, divided by 50 divided by 1000, which is the volume, and that gives us 2.4 times 10 to the minus 3 mole dm to the minus 3. This is the concentration at equilibrium, and the same is true for iron. To calculate Fe3+, we do the similar thing. We just use a different moles at equilibrium, as iron has a different one. So 2.38 times 10 to the minus 3 divided by 50 divided by 1000, which gives us 0.0476 mole dm to the minus 3, and that's the concentration. So now we must calculate Kc. In order to do this, we use the Kc calculation, which is shown here. Kc formula, which is shown here, where we do the products divided by the reactants. We must discard any solids because we don't use them in the Kc calculation. And we calculate Kc for this equation in the following way, which is that 0.0476 m, which is the concentration of the Fe3+ at equilibrium, divided by 2.4 times 10 to the minus 3 m times 2.4 times 10 to the minus 3 m, which is the concentration of the silver ions and the iron 2+ ions, and that gives us 8,263.8 moles to the minus 1 dm cubed. You have to work out the units each time, and you just substitute them into the Kc equation, and you can do that. And it really is that simple to calculate Kc.